So now the question begs, where can we use the dot product? And there's a couple of spots, but today all we're going to look at is one particular example. And that is to calculate something called work. Now I know work is something that is maybe foreign to some of you who are watching the video. You know, you come to class and you don't want to work, but work is actually something that I can measure. And but here we're talking about, you know, sort of the effort put forth to try and move something, and that's going to be something that we're going to call or define as work. So the definition here says the work done in moving an object through a displacement under an applied force acting at a certain angle. And unfortunately I can't be there to visually demonstrate this to you, so I'm going to try and explain it to you. If you need to move something like a couch, if you go up and stand next to it and stand upright and push it, you're not going to be really successful. What you need to do, and I'm sure we've all done this, is you bend your knees and you get down low so that the effort and the work that you're applying, the force that you're applying, is as close to the direction of motion as possible. So you want to decrease that angle so that most of your force is actually going towards pushing the couch. We're going to see where that applies in our mathematics. But for now, what we'll say is the work is calculated by taking the cross product of F, the force that you're applying, dot how far it goes, the displacement. So of course the amount of work if you're pushing a couch just a couple of meters is going to be different than if you're pushing it, you know, down a hallway. So here's your variables. You've got capital W for work, which is going to be in Newton meters or joules. S is your vector for displacement. F is the force that's being applied in newtons. And of course the angle between them is those two things. And the smaller you can make that angle, the more of the force goes through the direction that you're going. So you have that note. What I don't think you have is this example. So I'll give you a moment to copy this down, and you can do this in your book if you want. If we need to pause the video, go ahead, but just take a second to copy this down. So the example says an object is moving 15 meters along a horizontal surface by a force of 5 newtons at an angle of 45 degrees to the horizontal. Calculate the work done. So this is just a matter of applying our formula. We don't need to think too much about it, and see that I have all my information. I want to calculate work. It is apparently found by taking F dot S. We know the formula for the dot product is the magnitude of F times the magnitude of S and cos theta, where theta is the angle between them. It's just a matter of pulling the information from here. F is the amount of force, so in this case it's 5 newtons. How far we're doing this is in 15 meters. And the angle between them is 45 degrees. And so if we multiply, again, I do the cosine times 45 first, multiply it by 15, multiply it by 5, and we get 53. I think it rounds to 53, so I'm going to go 53.0 joules. And remember, joules is Newton meters. So your force has to be in newtons, and your distance has to be in meters. So therefore, the work done was 53.0 joules. So to go back to that idea about how you want to maximize your work, you want the angle to be really, really close to the angle of the direction. So if we were doing this exact same example, but our angle was 70 degrees, so you know, there's a big difference between the force in which it's being applied and the direction it's moving. So you're standing almost upright. Look at what happens to the math when you plug that in. The cos of 70 is a much smaller number. It's like 0.34. So when you multiply that by 75, it's like you're taking 34% of that, and you're losing a lot of it, and you don't have a lot of work accomplished. If we compare that, though, to if the angle is 20, so you really have made that area angle smaller, and now the direction of the force is much closer to the direction that the actual thing is moving, and you take the cosine of 20, the cosine of 20 is 0.9397. So it's like 94% of it. So when you multiply that by 75, you end up accomplishing a lot more. You get that 70.5. So it's good that the math does mimic what we have happening in real life. So you now have been exposed to the dot product. There's much more I'd like to discuss with you, but it doesn't really work through this video. But right now, just get comfortable with the formula. As I said, normally I would do these orally, and if the supply teacher is up for it, maybe he or she can direct the class to try and answer page 97, number 1 and 2 orally, and you guys can talk your way through it. It's not too bad. If not, just do it on your own, and we'll take it up next time I see you. And then for these ones, what we want to do is after that, just try page 97, 3 to 11. Numbers 3 to 5 for sure. Okay, make sure you do these ones. The 6 to 11, you can try them if you want. They're important, but not as important. And these ones for sure as well. Okay, so if you only have a little bit of time tonight, make sure you try 3, 4, and 5, 6, 7, and 8. Thanks very much.